6.5 Rational Functions. Now we've talked a little bit about rational functions. We've talked about the domain restrictions on rational functions, and we're going to bring that back in this lesson. But we're going to talk a little bit more in depth about them and take a look at some of the graphs. So a rational function is a function that can be written in the form f of x equals p of x over q of x, where p of x and q of x are polynomial functions. Q of x cannot be equal to 0. So even though q is not allowed to be identically 0, there will often be values of x for which q of x is 0. And we've talked about that when we talked about the domain restrictions on a rational function. These restrictions tell us about the graph and something called vertical asymptotes, which we'll define at a little bit later in the video. Consequently, the domain of f consists of all real numbers except for those for which q of x is equal to 0. Alright, so here are some graphs, some pictures of rational functions demonstrating the horizontal and vertical asymptotes in different positions. These functions move around as other functions did when we talked about transformations. Alright, so vertical asymptotes. The vertical line x equals c is a vertical asymptote of a function f if f of x increases in magnitude without bound as x approaches c. Examples of vertical asymptotes appear in figure 2. The graph of the rational function cannot intersect at the vertical asymptote. So these are the three different ways that you can see a vertical asymptote. Horizontal asymptotes. The horizontal line y equals c is a horizontal asymptote of a function f if f of x approaches the value c as x goes to negative infinity or as x goes to positive infinity. Examples of horizontal asymptotes appear in the figures below. The graph of a rational function may intersect a horizontal asymptote near the origin, but will eventually approach the asymptote from one side only as x increases in magnitude. So you can see in these pictures the horizontal asymptote serves as a boundary as x goes to negative infinity and as x goes to positive infinity. And then these other examples are pictures where it crosses over near the origin. Oblique asymptotes is something that we don't really look at in this class, but you will encounter them if you take calculus. An oblique asymptote is a non-vertical, non-horizontal line. It may also be an asymptote of a function f. Examples of oblique or slant asymptotes appear in the figures below. Again, the graph of rational functions may intersect an oblique asymptote near the origin, but will eventually approach the asymptote from one side only as x goes to infinity or x goes to negative infinity. Okay, so in calculus we explore what we call limits, and this part I'm going to kind of skip over it a little bit. I'll leave that to your calculus teacher to show you in more detail, but we talk about these limits as we approach from one side or the other. So as x approaches c from the negative side, from the left, we put a c to the negative, and as x approaches c from the right, we put a plus sign, a c is positive. Alright, so let's find some vertical asymptotes. First, let's go over a theorem. If the rational function f of x equals p of x over q of x has been written in reduced form so that p and q have no common factors, the vertical line x equals c is a vertical asymptote of f if and only if c is a zero of the polynomial q. In other words, f has vertical asymptotes at the x-intercepts of q. Note, we must always find the domain before canceling common factors, even if a zero is removed from the denominator when finding the reduced form. That value is not part of the domain. I believe that we will have that instance in the second example, but let's go ahead and look at the first example. Alright, so find the domains and the equation for the vertical asymptotes of the following functions. So finding the domains makes us find the asymptotes as well, so we're kind of doing both at the same time. So to do this, we do it like we did in the previous section, where we take the denominator and set it equal to 0 and solve for x. So x plus 2 equals 0. Subtract 2, x equals negative 2. Now remember from the previous section, this is the restriction on the domain. So the domain of f would be negative infinity to negative 2, close parentheses, union, open parentheses, negative 2 to infinity. Now this domain restriction, since nothing cancels out from top to bottom, this domain restriction is the equation for the vertical asymptote. And I want to caution you, whenever you're doing your homework, the software does require you to write the equation x equals negative 2. So make sure that you put x equals in your answer. The software will count it wrong if you forget to put x equals 2, or x equals negative 2. You need to put that x equals. Okay, so let's look at the next example. So again, we're looking for the domain restrictions. So we take x squared plus 2x minus 15, set that equal to 0. This one is factor friendly. X plus 5 times x minus 3. And then set our factors equal to 0 and solve. So x equals negative 5 and x equals negative 3. Now these are the domain restrictions. So the domain would be negative infinity. That should be a positive 3. To negative 5, union, negative 5 to positive 3, union 3 to infinity. Now looking again at our function, I see no common factors between the numerator and the denominator, so these both would be the equations for the vertical asymptotes. Okay, the next one. Set the denominator equal to 0. Add 1. So x equals 1 is our domain restriction. Negative infinity to 1, union 1 to infinity would be our domain. And now I see in my function that I can reduce this. I can factor out an x. And the x minus 1s will cancel, so my reduced function would be h of x equals x. So this function would not have any vertical asymptotes because the only one that we found is reduced. It's considered extraneous. And in fact, when you graph this function, since h of x equals x, it's a diagonal line with a hole in it at x equals 1. Alright, so now let's talk about horizontal and oblique asymptotes. So for that we have a theorem. So let f of x be a rational function p of x over q of x, where p is an nth degree polynomial with leading coefficient a sub n, and q is an mth degree polynomial with leading coefficient b sub m, and p of x and q of x have no common factors other than constants. And then the asymptotes of f are found as follows. Okay, so let's talk about what's going on here. They're talking about the degree of the numerator and comparing it to the degree of the denominator. We've talked about degrees of functions in here. So the degree is the highest power of x on top versus the highest power of x on bottom. The leading coefficients are the numbers in front of those highest powers of x variables on top and on bottom, and they're just using different letters to describe and separate them. So if the degree of the top is smaller than the degree of the bottom, is what the first one is saying. If n is less than m, the horizontal line y equals 0 is the horizontal asymptote. So let's look at an example of what that looks like, and we have one up here. So this example A, the degree of the top is 0 and the degree of the bottom is 1. So the degree of the top is less than the degree of the bottom. So we know the equation for the horizontal asymptote of this is y equals 0. Alright, number 2, if the degrees are equal to each other, the horizontal line y equals a sub n over b sub m is the horizontal asymptote. So whenever the degrees are the same, we take the leading coefficients and put the top one over the bottom one and reduce, and that gives us our horizontal line equation. And we do have an example of that up here. So the degree of the top is the same as the degree of the bottom, and the leading coefficient is 1 on the top and 1 on the bottom. So if I were to write the equation of the horizontal asymptote, it would be y equals 1 over 1, which is 1. So y equals 1 would be the equation of the horizontal asymptote. Alright, the third one is talking about something that we don't do in this class, but I'm going to tell you the part of the theorem anyway. So your focus is the first and the second one, but you need to know in your homework if it's got an oblique asymptote or not. If n is equal to m plus 1. So in other words, the top degree is 1 more power higher than the bottom. And I think we had that one here. So this is a 2 and this is a 1. So it is 1 more than the bottom. So this one would have an oblique asymptote. And I'm kind of lying there because when we reduce that, it does not have an oblique asymptote, but it did make a diagonal line. But remember that the theorem states that the rational function has to be in reduced form before you can determine this. But y equals g of x is an oblique asymptote for f, where g is the quotient polynomial obtained by dividing p by q. So we would have to use division to find that oblique asymptote. Okay, and number 4 you do need to know about. It says if n is bigger than m plus 1, then there are no straight line horizontal or oblique asymptotes for f. So in other words, if the degree of the top is more than 1 bigger than the degree of the bottom, like say it's 2 bigger or 3 bigger, then there are no straight line horizontal or oblique asymptotes. All right, let's find some horizontal asymptotes. So looking at f of x, I see that the degree of the top is the same as the degree of the bottom. The numerator does not factor, so I know that it's not going to reduce. So since the n is equal to m, that's the second rule. So y equals a sub n over b sub m, and in this case that's 1 over 1, which is 1. So the equation would be the horizontal line y equals 1. And just like with the vertical asymptotes in your homework, make sure you put y equals. Okay, the next one. This one, the degree of the top is 1 more than the degree of the bottom. So we know that this is going to be an oblique asymptote. And we don't cover that in this class, so we're just going to say it's got an oblique. Okay, the next one. I see that the degree of the top is less than the degree of the bottom. So that is the first rule. Let's go back to our rules. N is less than m. So the horizontal asymptote would be y equals 0. It doesn't matter how much smaller, it just matters that it's smaller. Okay, and then the last one, the degree of the top is 2 more than the degree of the bottom, so there are none. Alright, so for the graphing on this section, I decided that I was going to use the software to do it because you don't actually have to draw the pictures, you just have to know where they go. So we're going to do a couple of examples from the homework. So let's take a look at this first one. It says find the equation of the vertical asymptotes, if any, for the following rational function. So my suggestion is you pause the video and try to find it yourself, since we've already talked about that. Okay, I'm going to flip back to this, and we take the denominator, we set it equal to 0. Nothing's going to reduce, so I can add 8. So x equals 8 would be the equation of my vertical asymptote. Go back to the software, type x equals 8, and submit my answer, and I get the green bar, so I must have gotten it right. Alright, let's try this one. So it says find the equation for the vertical asymptotes, if any, for the function. Okay, so set the denominator equal to 0. Alright, so to solve this, I'm going to go ahead and add 64 to both sides. And this will give us the real solutions to this. There are some imaginary solutions to it, but we don't worry about those for the asymptotes. And I'm going to take the cube root of both sides. So I get x equals 4. Now, since the numerator does not factor, nothing will cross out, so that is indeed our vertical asymptote. So let's type that in, x equals 4. Okay, next we need to find the horizontal or oblique. And so for that we look at the power on the numerator and the degree on the denominator, and I see that the degree in the numerator is less than the degree of the denominator. So that is the first rule. So I know that my equation is y equals 0. Alright, so this one is an actual graphing, and this is what I wanted to talk about. Okay, so it says first plot the vertical asymptotes, if any, on the graph. So let's go ahead and transfer this over to my notepad so that we can find the pieces that we need. Okay, set the denominator equal to 0. And this one is factor friendly, but I'm just going to extract square roots. So x squared equals 64. Take the square root of both sides. And so x equals plus or minus 8. Now the numerator does, you can factor out a -1, but nothing will cancel out with the denominator, so we know that the x equals -8 and x equals +8 are our vertical asymptotes. There are 2 of them, and they want us to plot them, so we come over here and plot that one at -8 and this one at +8. Okay, and now plot the horizontal asymptotes. So let's go back to the notepad. So n is less than m, so y equals 0 would be our horizontal. So there is 1, and they want us to plot it, y equals 0. Okay, so now it's time to sketch the graph, and to do this we need to test values. Notice as I slide my cursor along the graph that parts of the graph light up. So we're going to plug in test values, like I would plug in -9, and I'm looking to see, am I going to get an answer above 0 or below 0. I'm testing to see positive or negative, so I know where to put my graph. So and in the center I might have to do a couple of test values to get enough information to make sure that I know what I'm doing. Okay, so in the first piece it's going to be one of these 4 pieces, you know, either this one, this one, this one, or this one, depending on its location. Okay, and the same is true for this region over here. And then this could be one of these 2, or it could be this parabolic shape, and it all depends on what values we get. So let's plug in some test values. So I'm going to do a little back and forth. So I'm going to plug in a -9 into my function. So I'm going to find f of -9. So it's -9 plus 1 over -9 squared minus 64. So that's 10 over 81 minus 64. And we're going to get a positive answer. We really don't care what the answer is, but let's go ahead and work that out. Okay, 10/17. So that's above the x-axis. So that tells me that the graph is going to go up here. And remember the theorems that we talked about at the beginning. As x approaches c, it's either going to go to infinity or go to -infinity. And since it's above the x-axis, it's going to go like that. Okay, so now let's test one on the far region C, because we should get the same result. Actually, no, we won't. Let's go ahead and do f of 9. So that's region C. So this is going to be negative 9 plus 1 over 9 squared minus 64. And so that's going to give us negative 9, that's negative 8 over 17. So that's negative, so that's below the x-axis. So over here, we're going to have this graph, because it graphed below. So now we need to do a couple of test values, and I encourage you to choose values away from the origin. It's tempting to use 0 because it's easy, but it's not going to give you the information you need. So I'm going to step out to negative 5 and positive 5 and see if it gives me the results I think it should. So let's go back and do f of negative 5. So that would be negative 5 plus 1 over negative 5 squared minus 64. So that would be 5 plus 1 is 6. And then 25 minus 64 is negative 39. And so that gives us 2 over negative 13. So that's below the x-axis. And now let's do f of 5. So that would be negative 5 plus 1 over 5 squared minus 64. Negative 5 plus 1 is negative 4 over negative 39. So that's positive 4/39, and that gives me the information that I needed. So that tells me in region B, on this side it's below the x-axis, and then on this side it goes above the x-axis. So that means that it's going to be this shape right here. So I'm going to select that region and pop it in there, and you can see that it does meet the requirements of the values I found. The negative 2/13. I know you can't really see that, but it's just below the x-axis, and then the positive 4/39 just above the x-axis. And that's how you graph them.